Hi team, today we're going to be talking about wave behaviors. In other words, we're going to talk about waves behaving rad-ly. We're going to talk about muons, why light refracts to be able to burn things with magnifying glasses, why you get ripples in water when water tries to move around large rocks, and why you hear all of that static interference on the radio. Our objectives for this lecture: describe and differentiate between reflection, refraction, diffraction, and interference. Describe the change in speed or wavelength for a refracted wave based on a diagram. And finally, predict the shape of a wave formed by. There are 4 types of wave behaviors we're talking about today. We're talking about muons reflection. A reflected wave just happens when a wave hits some sort of surface or boundary and rebounds off that surface in a different direction. This is the law of reflection. All right, you have a ray or a wave coming in, it hits a boundary, and it reflects off. The law of reflection states the angle at which the wave hits the barrier must also be the angle that the ray or wave reflects off that boundary. The other thing about reflection is that besides the direction, nothing else about the wave changes. Frequency, wavelength, and speed must all stay the same. The next type of wave behavior is refraction. This is what happens when light bends to be able to focus through something like a magnifying glass. What happens in refraction is a wave changes media. Now, what is it? It's just the material a wave is moving through. Today we'll talk about air, water, and glass, but really it can be anything that a wave moves. As the wave changes this material or media, the wave actually bends. Why is this the case? Well, because the wavelength changes as it changes material. For example, it's easier for a wave to move through deep water than it is through shallow water. As a result, that wave gets scrunched up in shallow water. Its wavelength decreases. As a result, the speed of that wave decreases, and this is what causes the wave to bend. The cool thing about this is we can actually tell which medium a wave moves faster in based on the wavelength. The longer the wavelength in a material, the faster the wave moves. In this case, we know the wavelength is longer in deeper water, and so the wave must move faster in that water. Another way to look at this problem is to look at the black boundary line between deep and shallow water, and the yellow line I've just inserted on this diagram representing the perpendicular to that boundary. If the wave moves slower, then the wave will bend away from the black boundary and towards the yellow perpendicular. This is true for all refracted waves. In other words, if your wave moves slower in the second media, aka shallow water here, it will bend away from the black boundary and towards the yellow perpendicular. The other way is true. So if you're moving faster, it will instead bend towards the black boundary. Here's an example. Does the wave move faster in air or glass? I notice as light travels from air to glass, it bends towards the perpendicular or away from the boundary. In other words, it slows down when it hits. As a result, it travels faster in air. Now I'd like you to try a problem. Pause the video now, try to answer the problem, and then press play again when you're ready to hear the answer. Did you get air? Air is the correct answer because, as you notice, the wave bends away from the boundary between air and water. You can also notice that the wavelength gets shorter in water, so it must travel slower in water and faster in air. Let's review refraction. When a wave changes media, it changes speed. This causes the wave to bend. Next, we're going to talk about diffraction. This is what when a wave passes through a slit or moves around, it causes a ripple effect. In other words, that wave is still bending, but unlike refraction, it's not bending because it's changing wavelength or changes speed. It's bending so that it can fit through that slit or move around that boundary. This is why you get ripples in your waves when you are at the beach and that water is bouncing off of rocks. It's also the reason that you can hear somebody who's shouting from another room, because that diffraction will allow the wave to travel around the door. The last type of wave behavior we're going to talk about is called interference. Interference you hear all the time on the radio when two different stations start competing. In this case, two or more waves are colliding and their amplitudes will add or cancel out. Let's look at what this actually means. In these two examples, the crests of two waves align. When they align, they create a larger amplitude. It doesn't matter if it's upwards or downwards. All that matters is that the crests of the waves are lining up. On the opposite hand, when waves' crests don't line up, those amplitudes will subtract or cancel out. In the first diagram, you see that the wave cancels out entirely and your resultant wave doesn't exist. You'll see in the bottom picture, those amplitudes just subtract and you get a wave that is smaller, but in the downwards direction because the blue wave is bigger than the red wave. Again, your amplitudes will add if crests align. Your amplitudes will cancel if their crests and troughs align. I want you to go ahead and try and this is an example. I'm going to now show you how to determine the resultant waveform from the interference of wave 1 and wave 2. Now, I noticed that the crests and troughs align. As a result, the amplitudes of these two waves will add. I notice that for my red wave, it has an amplitude of 2 units. For my blue wave, it has an amplitude of 4 units. If I add 2 and 4, my resultant wave should have an amplitude of 6 units. That's exactly what this wave looks like. A new green wave is formed that has an amplitude of 6 units. Now I'd like you to try this problem on your own, and I've given you some multiple choice answers that you might see on a common assessment. Pause the video now and try to determine the correct answer. Did you get answer A? Answer A is correct. The reason answer A is correct is because when wave P and wave Q collide and interfere, the portion of wave Q that has an amplitude that aligns with wave P will cause a large hump. That's where you get the large rectangle from on answer A. The second half of wave Q that has a trough mismatches with that portion of the crest on wave P. As a result, those just cancel out and become nothing. So A is the correct answer. Just so you know, that was straight off of last year's third common assessment, and it was a difficulty level of 5. So if you understood that problem, you are good to go. We're done with our new information, but I just wanted to let you know. If you're in pre-calculus, you're currently studying sequences and series. An important series in science and engineering and math is something called a Fourier series. This is important for taking electrical signals, like those you'd send out of a radio tower, all right, and you represent them as just a sum of interfering sinusoids. Now, I know that's really, really nerdy, but it's still cool. So let's look at what we've learned today. If you're still confused, go back and replay this video. If you feel like you're awesome, you've got it, that's great. If you feel like you want some more examples, there are some extra YouTube videos that you can watch as examples of these phenomena posted on the course website. Thanks, and I'll see you tomorrow.